We will wrap up our study of integration by examining two types of improper integrals. The first type of improper integral contains an infinite limit of integration, and the second type contains an integrand with an infinite discontinuity, also known as a vertical asymptote. In this video, we will focus on the first situation, integrals over infinite intervals. Now, let's suppose that our integrand f of x is continuous, and when we see a and b, we'll assume that they represent real number constants. There are three situations that we may encounter with infinite limits of integration. The first is the integral from a to infinity of f of x dx. What makes this integral improper is the infinite upper limit. Now, if we think about what this integral represents, it's going to be the area between the curve f of x. So if you look at the graph on the right, this may represent the curve f of x, and we're determining the area between the curve and the x-axis from the finite x value a to an indefinite upper limit. That is, x is going to infinity. When we determine the antiderivative and begin to evaluate it at the upper and lower limits of integration, we have learned that it is not proper to plug infinity in for x, because infinity is not necessarily a constant. It is a concept representing a quantity increasing without bounds. So in order to make our analysis legal and proper, we're going to rewrite that infinite upper limit as a constant and then introduce the limit operator as the limit as b approaches infinity then represents the improper integral. Now, this situation may occur on the lower limit of integration as well. Consider case 2, the integral from negative infinity to b of f of x dx. Again, what makes this integral improper is this infinite lower limit. This integral represents the area between the curve y equals f of x and the x-axis from an indefinite lower limit to a finite upper limit of b. In order to make this proper and legal to evaluate, we're going to change that lower limit from negative infinity to a and then introduce this limit operator, the limit as a approaches negative infinity. Those operators will allow us to properly determine the value of the definite integral. The last situation that we may run into is a combination of the first two. Let's suppose we want to find the integral from negative infinity to infinity of f of x dx. Well, this represents the entire area under a curve from negative infinity to infinity. So we are going to take that interval from negative infinity to infinity and split it anywhere in the domain at some point called c. Then we will evaluate the definite integral between negative infinity and c, and then the integral from c to infinity. So we'll break it up into two different pieces. Now, as far as the lower half of this region goes, we're going to rewrite the lower limit, which previously was negative infinity, as a, and introduce this limit operator, limit as a approaches negative infinity. And again, c can be any point in the domain where the function is defined. Then we're going to go from c to new upper limit b, and remember the previous upper limit was infinity, so we will properly express that with the limit operator. Now, it is possible that when we evaluate these improper integrals that we get an infinite value. That is, the limit technically does not exist. So if the limit does not exist, we say that the integral diverges. If the limit exists, then it displays the value of the definite integral. So let's try a couple of examples, starting with example 1. We want to find the integral from 1 to infinity of natural log of x over x dx. What makes this integral improper is the infinite upper limit. Now, before we deal with the infinite upper limit, let's just consider our process of integration. In order to find the antiderivative of natural log of x over x, we would need to make a u substitution. Hopefully you will recognize that u equals natural log of x would work, because du is 1 over x dx. So I can rewrite this integral as u du. Now, we're going to need to update both of our limits of integration from x values to u values. Let's start with x equals 1. When x equals 1, we know the relationship between u and x is here. When x equals 1, u is equal to natural log of 1, and clearly that's 0. So my new lower limit for u is going to be 0. Now, if x is infinity and this x goes to infinity, natural log of an infinitely large number is also infinitely large. So the upper limit will stay as infinity. But we do need to make this rewritten with proper notation. So we will introduce a limit operator. We're going to rewrite this as the integral from 0 to b of u du. And then we'll make it equivalent to the previous line by introducing the limit operator, the limit as b approaches infinity. So this upper limit is still an infinite upper limit, but it's expressed with proper notation. Now let's go ahead and proceed with the integration. We'll carry this limit operator until we actually execute that limit. So we have the limit as b approaches infinity. That is a pending operator. Now we're ready to execute the integral. So the antiderivative of u is 1/2 u squared, and we need to run this from 0 to b. So like we normally do, we're going to plug in our upper limit. First, we have 1/2 b squared, and we're going to subtract our antiderivative evaluated at the lower limit. Clearly, that second term has a value of 0. And if we calculate the limit as b approaches infinity of this first term, infinity squared is also infinity, so the value of this limit is infinity. Technically, however, we can say the limit does not exist. DNE is abbreviation for does not exist. We just describe the behavior of that function by saying it is tending towards infinity. But technically, the limit does not exist. Therefore, we can say the integral diverges. If we want to interpret that geometrically, that simply means that the area between the curve given by this integrand and the x-axis from 1 to infinity increases without bounds until it is immeasurable. So this particular example ended with a divergent integral, but not all improper integrals are divergent. Let's look at another example. We have the integral from negative infinity to infinity of 1 over x squared plus 1 dx. Notice this is an improper integral because we have two infinite limits of integration. So what we need to do is to divide this up into two integrals. We're going to split it somewhere between negative infinity and infinity, and then introduce limit operators to make our notation proper. So a convenient place to split this integral might be 0. Let's go from negative infinity to 0 of 1 over 1 plus x squared dx, and add this to the integral from 0 to infinity of 1 over 1 plus x squared dx. No u substitution, no variable change is going to be necessary in evaluating the antiderivative. Notice this is going to lead us to an arctangent function. So we can go ahead at this point and introduce our limit operator. Now we're going to need a lower limit. I'm going to just call it a. We're going to let a approach negative infinity. And then we can simply label that lower limit as a. No change for the upper limit, and everything else stays the same at this point. Let's work on our second integral. We can make this one proper by introducing a limit operator. For the upper limit, I'm going to use b, and we'll allow b to go to infinity. No change is necessary for the lower limit, but we are going to rewrite that upper limit as b. And then we can record our integrand, and we're ready to find the antiderivative. So before we execute our limit, let's go ahead and execute the integral. The antiderivative of 1 over 1 plus x squared dx, That's going to be 1 over a, or 1 over 1, that just reduces to 1, of arctangent x over a, or in this case, x over 1. So we're going to run that from a to 0. Notice we get the same antiderivative here, arctangent of x, and this one is, oops, I lost my limit operator. Let me go back and pick that up. Limit b approaching infinity, arctangent of x, and this one is going to run from 0 to b. So let's plug in our upper and lower limits. We have the limit as a approaches negative infinity of arctangent of the upper limit 0 minus arctangent of the lower limit a. We'll do the same thing for this second term. The limit as b approaches infinity of arctangent of the upper limit b minus arctangent of the lower limit 0. First of all, let's recognize that arctangent of 0 is 0. That is tangent of 0 degrees, or tangent of 0 radians, equals 0. So in both of these cases, we're going to lose that term. So we can focus on evaluating our limits at infinity. Notice we're going to need to evaluate the limit as a approaches negative infinity of arctangent of a, and the limit as b approaches infinity of arctangent of b. So we need the limit at both positive and negative infinity for arctangent. Now, if you don't know that right off the top of your head, the graph can certainly be a helpful aid in determining those limits. We have previously examined the graph of arctangent. It's the reflection of the tangent function across the line y equals x. In the same way that ordinary tangent has a vertical asymptote at negative pi over 2 and pi over 2, arctangent has horizontal asymptotes at negative pi over 2 and pi over 2. So the pattern of the graph looks something like this. So if we want to calculate the limit as the argument goes to negative infinity of arctangent of x, we can observe from the graph that as x approaches negative infinity, the function levels out over this horizontal asymptote at negative pi over 2. So the limit as a approaches negative infinity of negative arctangent of x will be negative pi over 2. Notice the first negative comes from our analysis here, and then the second negative is simply the value of the limit that we're observing from the graph. Similarly, to calculate the limit as b approaches infinity of arctangent of b, we can say what happens to the graph as x goes to the far right without bounds. Well, we know that this curve is going to level out underneath its asymptote, and the value of that asymptote is pi over 2. So the limit as b approaches infinity of arctangent of b then is pi over 2. So if we evaluate this sum, we have pi over 2 plus pi over 2. That gives us a value of pi. Since we obtained a finite value for these limits, we say that the integral converges. And in fact, we can make an interpretation that the area between this curve and the x-axis for the entire domain from negative infinity to infinity is finite. It has a value of pi square units. Now, the original problem didn't say we're calculating area. We're just attaching it to a geometrical interpretation. If it did say find the area, we would want units squared here. But since we're just calculating the value of a definite integral, we'll report the value as exactly pi. Kind of interesting that we got pi for the answer there. So this is the first type of improper integral, that is, integrals with infinite limits of integration. In the next section, we'll consider how is this useful? Where might we apply this in certain aspects?